go back to, let us go back to this part here. So I will come back to this to explain about these things. So this is the part that we want to get the amplification factor for bending moment. Now, bending moment for this case of beam column, which happened at the midspan there, you can easily obtain, you make a cut section here, then you can find what is the maximum bending moment happen at the midspan, and it is given by these equations. So this equation shows us that when you have P, then because of the bending, you have delta, and there is an additional moment, which is what we call, what is given by these terms here, P delta. So this is one of the effects of having P. It causes additional moment on top of the moment caused by Q. So now, if we go further from here, just substitute the delta from equation 3.13, which is this. Then we simplify it to this first. And further, we get to this. So QL over 4 multiplied with this. Now, QL over 4, further, and this one further, we just make it into this expressions multiplied with QL over 4. Now this QL over 4, we represent this again as M subscript 0, and this M subscript 0 is the maximum moment that will exist if no axial force were present. So you can easily confirm that this QL over 4 is the maximum moment in the beam caused by a point load acting at the center. So that is where we come to these terms here now, 3.18. 3.18. So 3.18 is the equation showing the effect of having P on the beam column acting by Q at the midspan. So it is equal to the moment without P multiplied with amplification factor. If we compare 3.13 to 3.18, they show similar things, which is the existence of P is going to cause the moment, in this case, the maximum moment, to amplify. So equation 3.18 class is the effect of axial compressions on the bending moment. And it is very similar to 3.13. So if you look at 3.13, then and look at 3.18, the moment that exists in the absence of axial compression is amplified by the presence of an axial load. Again, we see that here, this 1 minus 0.018 over P over critical, 1 minus P over P critical, if you compare with the delta, which is equal to delta 0, 1 over 1 minus P over P critical. So you can find very similar pattern of expressions here. Only thing in delta, it is 1 on the numerator and denominator is 1 minus P over P critical. But in this case, it is 1 minus 0.18 P over P critical divided by 1 minus 1 over P critical. And if we look at this denominator and this denominator here, they are the same. Okay. So there is a similarity between the amplification factor for moment and the corresponding amplification factor for deflections. Okay. Now, before we go to the next case here, to see the derivations of amplification factor for beam column with distributed lateral load, I would like to go back to this previous page here, this diagram here. Now this diagram class is plot using these equations. Delta is equal to delta O1 over 1 minus P over P critical. Okay? So remember here, this is for a beam simply supported, and there is a mid-span load Q. So this is L over 2. Okay? And the delta 0 here is Q L cube over 48 EI. So when we plot this, okay, so the figure A here is plotted by fixing the value of P over P critical, fix the value of P over P critical to different values. Shown here, P over P critical 0, which is no axial force, then increase to P over P critical 0.4, then increase to P over P critical 0.7. Then with that ratio of P over P critical, then we increase the Q. We increase the Q. So we set here different ratio, then we increase the Q. Then we can find the corresponding delta. So this is the outcome of the plots. Q versus delta. Q versus the delta. So delta here is, if I can draw here, delta here will be reflection here at the midspan delta. So here it shows 3 cases of P over P critical. So let's look at what is the meaning of this graph here. Now as P increase, for this case P is equal to 0, delta also increase. So for second graph here, when P is equal to 0.4 P critical, which is P over P critical is 0.4 now. P is 40% of P critical acting constant at the beam, on the beam. So Q over delta is given by this straight line. So it shows again that Q increase, delta also increase. And we go to the third graph here, where the P over P ratio is increasing further. So, but if you look at this graph here, then we show that we can see that the slope of this graph, which is the slope here, the slope here, and the slope here, the slope is decreasing. The slope is decreasing. Okay? So one of the things that we can get important, a conclusion that we can draw from this graph here is that if a beam column is subjected to Q and P at the same time, is subjected to Q and P, okay, and if at different level of P, we fix the P at different level, then we increase the Q, then the effect of having P here will be to reduce the stiffness, to reduce the bending stiffness of that member. And why we say it is reduced is because the slope, the slope of this line here, the slope of this line and the slope of this line represent stiffness, bending stiffness. So because the slope is decreasing, meaning that the stiffness in this case, when P is 0, the stiffness in this case where P is 40% of P critical is decreasing compared to this, and increase further to 70% is decreasing even more. Okay. So this is one of the important things that we can draw from this graph. Now, before I go to graph B here, so it's important to note here that when we apply the load P here on this beam column, it is assumed to be constant. It is assumed to be constant, then the Q increase. So P constant at 40%, P critical, then we apply the Q. P is constant at 70% of the P critical, then we apply the Q. So this is the case for graph A, and all the graph here are straight line, linear. Okay. Now, if we go next to this graph here, which is also obtained from these equations, but the difference here is that we plot P over P critical versus delta. Here we plot Q versus delta. And there are two graphs here, which is one the dotted line and the other one is a solid line. Now, the solid line one here shows that Q constant. So here means we apply Q constant at certain level of Q to the beam column, then we increase the load P. So the load is changing, the actual load is changing. So this is the solid line here. And the dotted line here is we increase the Q, at the same time also we increase the P. So both Q and P increasing. So how does they increase? So sorry, this is the dotted line here. So we increase Q proportional to P. So we fix the proportions, we increase them. So here, the main thing is P increasing, changing. Here, P constant. Q changing. Here, P increasing, Q can be constant, Q can be changing, but P increasing. So when P increase, so you can see a very different behavior here is compared to this. When P increasing, so the response of the beam column become non-linear. It is not a straight line here anymore. So what are the conclusions that we can draw by looking at this graph A and B here is that the deflection of a beam column is a linear function of Q. Although you have a P here, if P is constant, then you still get the response linear. But if P is changing, then the response becomes non-linear. So again, the deflection of a beam column is a linear function of Q, but a non-linear function of P. So this is graph B here. Linear function of Q, this is graph A here. If both P and Q increase simultaneously, which is in this case here, shown by this dotted line here, the load deflection is non-linear. So as long as P is kept constant, you increase the P, so the behavior is still linear. If the P is not kept constant, you increase the P, then either Q constant or Q changing together with P, then you get non-linear response. So this is the important things that you need to take note of. So deflection of a beam column is a linear function of Q, provided that P is constant, but a non-linear function of P. That is, if P is increasing. So this is being explained here. So this is being explained here. Okay, so you can refer to this again, where I have already summarized using the PowerPoint just now.